We were discussing platform based design in the last class. Platforms provide us with a set of possible architectures to be explored for designing an embedded system. Today we shall continue that discussions. In fact, platforms enable, as we have already seen, software and hardware reuse. We would like to reuse as many hardware as components because that give us a advantage of knowing their performance statistics like power consumptions as well as the time taken to do a particular computation on the hardware block. We would like to use software libraries wherever possible, and we can do that by making use of the software platform which can be accessed for an application through a API. And the software platform makes use of an underlying RTOS kernel which simplifies design of multitasking system. So these are the basic features of platform based design approach. So related to this is that when we are starting from a functionality and gone into a task graph, the question is how do you map your task or your application to a platform? And one aspect of the mapping is the mapping onto the hardware architecture of the platform. So we have to keep track or know about the system topology, requirements about the different processing elements, what are the different kinds of communication channel available. There may be constraints in terms of communication channels. In fact, we have seen in the last class an example where we might design a platform around ARM where AMBA bus provides the communication interface, and that may be a constraint. But we have to do the design keeping in mind I have got the AMBA bus for communication. On top of that, there are software services. So the software services have to be made use of to coordinate the different functions which are being performed on the different hardware blocks, as well as for invoking those functions through your software services. The first question that comes up is how many processing elements do you require for a given application? In fact, this might lead to also the choice of the platform. If we are talking about using one big CPU, then obviously we might like to go for a platform which has got one CPU along with maybe some amount of programmable logic, which may be through your FPGA block may be implemented, or we might not require even that programmable hardware. We can build in the behavior completely using software. So in that case, the instance of the platform would be a particular software running on a big CPU. But critically, that depends on your time constraints. In fact, if you go back to the example of your camera design that we had considered, we are not being able to do the design using only 8051 simply because I had the timing constraint that the camera should be able to take the next snap within 1 second, and I cannot do compression of the image using your 8051 even when I am using additional logic on FPGA blocks. So tight deadlines in many cases are also incompatible with multitasking when we really have the deadlines, and deadlines are universally to be obeyed in a real time application. So what we need? We need to map tasks now to different hardware units. Some tasks may be to one CPU, other tasks to maybe a dedicated hardware unit. Similarly, tight communication deadlines discourage shared communication links. So in that case, we might need to build dedicated communication link using the configurable logic facility available on our platform. So, therefore, what would be the reasons for having dedicated unit? We shall have dedicated units only when the shared unit is not fast enough to meet our timing constraints as well as our deadline requirements. In fact, what we have found is that even when if I use rate monotonic scheduling, the utilization of the processor asymptotically approaches about 69%. So, what it implies? It implies that when you really have hard deadline constraints, using a simple CPU and trying to use that CPU optimally by following a proper scheduling approach will not yield results if your constraints are tight enough. So, under those circumstances, you have to go for dedicated unit. Also, there are overhead effects. As I have told you, in a software platform, my RTOS kernel can be made use of for managing the concurrent model, but each task will correspond to a process in RTOS, and there would be context switching. The context switching overhead can actually affect my timing constraints. Because of the context switching overhead, I might not be able to meet my timing constraints, okay, when we are using one CPU and mapping multiple tasks on that CPU. At the same time, there can be cache thrashing. That means, when we are switching from one task to another, I might need to reload the cache memory. So, there will be miss and hit, okay, at regular succession. Okay. So, when I am trying to access pages corresponding to one task, I shall encounter a miss. I have to reload, and there for the task for a small time period, I might have the pages in the cache, but whenever there is a task switch, I might not get those pages on the cache and there will be miss. The moment I have got cache thrashing coming into the picture, we are paying for performance, and not only performance, we shall be paying for energy, okay, because I need to transfer the data from main memory to cache. So, energy budget will also increase. So, under these circumstances, it may be a good decision to go for a platform which provides a support for multiple CPUs, maybe multiple ALUs, okay, as well as you might like to have a dedicated FPGA block where you would like to implement a specific functionality. So, that FPGA block in that case becomes a dedicated unit. So, therefore, the question comes up is what kind of processing elements, hardware versus programmable. Now, it depends on what kind of algorithms that you are making use of. In fact, in both the cases, if you look into it, if it is a programmable option, that means if you have a multiple CPU and you would like to implement a certain functionality on another CPU, the entire implementation is software based, okay, and there you need to have efficient algorithms. But if you are looking for a dedicated hardware to be built for that purpose, then you got to have an algorithm which can be translated easily to an efficient hardware implementation. Not all algorithms can be directly mapped onto hardware. It might require some work to map it into an hardware, and you will be using possibly VHDL, okay, to code that hardware algorithm for the target dedicated unit. In fact, when you are using a programmable CPU, the chip vendor selection usually limits the choice. In fact, you cannot have all possible kinds of combinations. So, if I go for TI's OMAP, I know what kind of CPUs are available and how the heterogeneous task graph for an application should be mapped onto the CPUs, taking into account their characteristic features. And what you would like if you are going for a multi-CPU platform to maximize parallelism. and that would give you the maximum benefit. But there also you have to keep in mind that when you are looking at a task graph, the alternate branches of the task graphs are getting mapped to two different CPU. So, the total time delay would be decided by the time taken for the longest branch. So, when you are doing an allocation, that point has to be kept in mind to make sure that finally you satisfy the timing constraints. We are looking at one problem, okay, one aspect of this platform based design, where we are having, let us say, a CPU along with some kind of a programmable logic. The question is, we need to have some functionalities to be implemented in hardware depending on my timing constraints. Now, you have generically two basic approaches. If you really have a soft core, you would like to modify the CPU, add on new instructions and get something done. On the other hand, your other approach could be, if you are not having a soft CPU or a soft core based platform, you might be having a hardcore CPU with a programmable logic on the platform. Then you would like to design the accelerator, that means a particular hardware function to accelerate one bottleneck that you have figured out. So, if you go back again to the camera example, we have found that DCT was the bottleneck. So, we might like to use this FPGA block to implement DCT to remove that bottleneck. So, we are not modifying the CPU by any sense, but we are implementing a special functional unit, okay, and that in many a times we refer to as accelerators. In general purpose computers, you do use very commonly graphics accelerators, which accelerates graphics data processing for the purpose of realistic image synthesis on the screen, which you need for variety of applications including games. So, accelerator provides accelerated option. So, how do you go for such an accelerated implementation? We can look at a possible implementation platform, and we are just looking at one example platform which is actually available commercially. In fact, this comes from ARM manufacturers. So, what we say, ARM integrated logic module. Okay. So, here you have got a basic ARM processor based card, which may be an ARM 9 based card if you are looking at ARM 9 integrator, to which an FPGA accelerator board can be plugged in. Okay. The FPGA interfaces to the ARM processor via AMBA bus, okay, via AMBA bus. So, here the communication is fixed. The FPGA can use AMBA bus to connect to SRAM and IO devices contained on the integrator board. So, the integrator board is basically your hardcore host CPU, and this accelerator board is the basic hardware framework on which you will be implementing the required function. Okay. And this accelerator makes use of the same AMBA bus to communicate with the processor, as well as for making use of the memory and IO devices. Now, what are these FPGAs really? If you are trying to design a function, we should know what are these FPGAs. In fact, FPGAs are in a way a programmable fabric that can be dynamically reconfigured. In fact, this point we had looked at when we looked at reconfigurable SOCs. So, basic job now turns out to be mapping of your task to FPGA. Typically, only the time consuming computations are mapped, the computations which are basically bottleneck. So, one way to identify such computations is by which process? We can actually compile the entire task by encoding it maybe in C or a procedural language, compile the entire task, run it on the simulator of the CPU, profile the code, find out the parts of the code which are actually consuming maximum time, and figure out whether the code is really violating the timing constraints. If it is violating the timing constraints, you should identify from the profiled code the bottlenecks. The functionalities implemented in the bottleneck should really be mapped to FPGA. The computation in this case have to be expressed in languages like VHDL. Okay? So, that means if that is a software algorithm, it has to be mapped to a sequence of hardware computations or hardware operations, which can be encoded in a language like VHDL, which enables you a behavioral as well as register transfer level, also interconnect level specification of your computation. But the issue now turns out to be is that you have expressed your computation, but that computation has to be mapped among the logic blocks of the FPGA, because FPGA is what we said is a programmable fabric. In a sense, it contains a set of programmable modules. We shall see examples of those soon, but let us try to understand what FPGAs are right now conceptually. There will be a set of logic blocks. So, when you are writing a computation in VHDL, it comprises of a set of functions. Now, these set of functions have to be again partitioned and mapped into the FPGA blocks. For that, we need to use what we call place and route tools for partitioning the circuit, which you can actually synthesize from your VHDL description of your computation to different logic blocks on the FPGA. And typically a structure of this kind of an FPGA based board is FPGA plus memory on a peripheral board. This memory can have the data which is used by the computation that the FPGA is expected to do. In fact, you can get FPGAs in various forms. FPGAs can be, some FPGAs can be programmed only once. So, once it is programmed, it cannot be changed. There are other FPGAs which are reprogrammable FPGAs, which actually can form the reconfigurable component in a platform. So, what are really FPGAs? FPGAs, we said, is a configurable logic, and here we are showing a very simple example. Okay? In fact, this is a basic logic block. You have got a 4 input LUT, so it is a kind of a combinational circuit. Okay? This is another 4 input LUT. So, depending on the 4 inputs, you can synthesize any 4 input function. The basic idea is that. And this is a multiplexer. Depending on control inputs, you can choose the functions from these 2 blocks, and these are the flip flops. So, this forms what is called a basic logic block, which consists in a way a set of lookup tables connected by a programmable interconnect. In fact, this multiplexer tells you which one is to be connected to the flip flops, and subsequently these blocks themselves can be connected in a programmable way to realize a computation. So, effectively what we are seeing? We are seeing that we have got a set of combinational circuit blocks, we have got a set of flip flops registers, and if I have these set of blocks and if I have the freedom to connect them in any way I would like, I can synthesize any combinational or sequential logic functions. And any hardware unit which is doing any kind of a function, therefore, can be synthesized through these kind of FPGA blocks. In fact, this is showing you a organization where we say that this is a logic block. These are effectively your IO blocks, and these represents the interconnect pattern, and these interconnection patterns it should be possible for us to program. So, typically therefore, an FPGA consists of following blocks. What we call is IOB, okay, that is input output blocks. Then you have got configurable logic blocks. Okay. These are the basic units to which your functions are mapped, and then you have got programmable interconnections. So, if we look at this is one FPGA, there are various manufacturers. We are looking at a Xilinx FPGA organization. So, this is exactly what you have got. You have got your configurable logic blocks. These are your programmable interconnects. So, how this will be connected, these can be actually programmed. Okay. And these are called long interconnects. These are your I/O blocks. Depending on your interface to the external world, these I/O blocks can be set. So, in fact, what is your programmable part of the logic? You actually can synthesize what these logic blocks can actually do. You can synthesize how these logic blocks have to be connected. Also, you can specify what kind of inputs should come into this logic block. So, that means using these blocks you have the ability to synthesize any kind of a circuit, and in fact SRAM cells are used to encode the configuration. When I am using SRAM cells to encode the configuration, which essentially means that if I change the SRAM data, I can get another configuration for this FPGA block. Let us look at an example CLB. If you look into here, I had already given a simple example. Here this is an example from an actual FPGA block. See, these are your 4 input lookup table implementations, which can synthesize any 4 input function. This can synthesize another any 4 input functions, and this is can synthesize a 3 input function. Okay. This can synthesize a 3 input function, and these are all multiplexes. Okay. And this input is basically your control input. That means using these inputs, okay, you can actually configure the system to synthesize different functions. If you look into this path, this actually tells you that whether this H1 is to be computed or not. Okay. In fact, the other informations which are coming out, that is your control inputs for your multiplexers and others, that also can be provided through these inputs. Here we have got the flip-flops. Okay. These flip-flops also have got set reset logic. They have also got the set reset logic, and they can be positive or negative edge triggered, synchronous or asynchronous, and you can provide the clock as well. Okay. Clock as well to these blocks. Okay. So, effectively what you are finding here is that you can synthesize logic functions, both combinational and sequential logic functions, even using a single FPGA block, okay, logic block. And you can synthesize obviously more complex functions when you connect these logic blocks together. Okay. So, effectively what you have got therefore a kind of a programmable fabric to synthesize any logic functions. So, in a way you have got what we call hardware programmability. Try to distinguish between the software programmability with respect to hardware programmability in terms of your platform based design. FPGA is providing with you a feature for hardware programmability. Okay. That means you can synthesize different functions by selecting which 4 input function to be implemented here, selecting how these muxes should be configured, multiplexers should be configured, figuring out or telling how these registers should really behave. And this becomes a programmable switch. Okay. This is a programmable switching matrix, okay, which is connecting the different CLBs together, and I can load in fact the data onto this matrix to decide on the interconnection and as well as for configuring maybe the CLBs, okay, because that would provide various kinds of control input. So, it will come from one CLB to another and it can be an input as well. So, this switching matrix determines the interconnectivity between the logic modules. So, that means when you are looking at the problem of designing an accelerator, it means what? The function which is to be implemented in hardware has to be mapped to FPGA. So, if you are using mapping tools straight away, then what you need? You need to encode your function in VHDL, use the tools to simulate and find out first whether your VHDL code is correct or not. Second thing, whether your VHDL code is synthesizing a circuit which can satisfy the timing constraints. If you are satisfied with that, then you do the mapping onto that FPGA block, and once you have done the mapping, you have got an FPGA based implementation of the function. So, therefore, if I now have got that implementation, I have got an accelerator. The question is that implementation also implies that you have designed the glue logic using which the accelerator knows how to communicate with the CPU and memory. So, typically what happens is the CPU puts in a request to the accelerator, okay. Accelerator performs the function. In fact, it can access the data, because to perform the function it would need to access the data. So, it will access the data which is in the memory, okay, and can write the result back to the CPU or the memory, or it can write the data onto the memory and inform the CPU that it has written the data onto the memory. This is how typically an accelerator functions, and this interface forms part of your glue logic. Now, this takes us to the software aspect of the whole design. I told you that a platform based design is just not hardware design, but software design as well. The question is, if you have got the CPU and accelerator, so how should the software be designed to manage these two things? Okay. So, typically what we say is that these kind of configurations would require a multi-threading implementation. Why multi-threading? One of the threads can manage the CPU's task, the other thread can actually look at the accelerator. Obviously, the thread is not really getting executed on the accelerator, but keeps track of the job being done of the accelerator. Because what would be really the communication modality between the CPU and accelerator? Will it be a blocking communication? That means the CPU, we have found that CPU typically requests the accelerator to do the job. So, if the CPU is requesting the accelerator to do the job, will CPU get blocked? If I really do not have a multi-threading kind of an environment, that CPU can actually be blocked and wait for the result to come back from the accelerator. If we are really looking at a multi-threaded implementation, then thread can be blocked, but CPU can be used for servicing some other thread. CPU can be used for servicing some other thread. So, typically a kind of an accelerator based implementation would like a software model which is a concurrency based and a thread based. So, that configuration can come from your API definitions, because through your APIs you will be managing the concurrency models, okay, and these concurrent threads will be linked with the different tasks which are being done on the CPU with the help of the accelerator. Please try to keep this in mind, that although this task is getting mapped onto the accelerator, CPU has to keep track of the data. So, that task is being mapped to a thread which is running on the CPU. So, actually CPU in a way is still shared, although the actual computation is being done by the accelerator. Along with it, also there are issues of memory design. Okay, what kind of memory system you would like to have? cache. If it is cache, then what is the size, what are the number of sets to be used, what is the block size to be used, because that has to be determined depending on the characteristics of your computation, because you would like to optimally select these numbers such that your cache miss is minimized, and in a way your energy consumption is minimized as well as the cost does not go up. If you are using only say cache like memory and nothing else, okay, then obviously your cost would go up. So, you have to optimize on the cost as well. Okay. Also on on-chip main memory, what is the amount, type, because banking of the memory becomes an important issue, because when we discuss a power architecture, we have told that if we can optimally arrange memory into banks, then your power can be saved, because your leakage current over individual banks are much less. Okay. Your capacitive current to your capacitive load also gets less, because there are less number of lines to drive. And there may be off chip main memory as well, which actually has got the code, that means your flash memory. So, what kind of flash to be used, what kind of organization to be adopted. So, these issues leads to what is called your memory design on the platform. But obviously, if the platform gives you a fixed set of choices, you have to make choice among those options only. Okay. But it may so happen that platform has a facility to interface external memory. So, you have the advantage to make a choice about your memory. Okay. So, then the memory architecture gives you another dimension of exploration in the design space. Okay. We have looked at one aspect of exploration, that is use of the CPU and the accelerator. The memory architecture provides you with the another space of design exploration. In fact, with this background, let us look at some of the existing platforms on which these kind of strategies can be used and applied. In fact, there are a number of these kind of hardware platforms which are today available, where you have got microprocessors and configurable logic. In fact, the ARM example was ARM integrator board with a separate FPGA board. Now, we are talking about maybe a single device which can have microprocessors as well as the configurable logic. In fact, there are two kinds of devices which you get. One is based on soft core approach, another is based on hardcore approach. And in a typical soft core approach, the basic idea is that you have got the FPGA, and on the FPGA you actually synthesize the processor itself. And in a hardcore approach, you have the processor, with the processor you have the FPGA block, just like the accelerator kind of a design that we had talked about. So, conceptually the block diagram looks something like this. You have got here the configurable logic block, you have microcontroller and other processing elements, and this provides the memory. So, let us first look at the soft core approach. In fact, if you remember, we discussed that in the last class also, that we can, if I am doing a platform based design with a soft core availability, I have got certain freedoms available with me in terms of choosing the processor architecture, choosing the IO devices, choosing even the register set which a processor can have. So, these could be the parameters of say VHDL based design which can be played with to make a choice about the architecture. In fact, in this case, when we have the soft core based approach, you basically get a big FPGA block, and you use a region of FPGA to implement the microprocessor core. In fact, again if you go back to the camera example, we said that 8051 is available with us in a VHDL form. If it is available in a VHDL form, if we have this kind of a soft core approach, and if we have a parameterized form of 8051 architecture, then we can play with the parameters to get variations of 8051 to meet our requirements. Okay. And that gets interfaced here. So, once we get one particular configuration, what we are getting? We are getting an instance of the platform. The platform as such can implement, if I start with 8051 as a VHDL, can implement a variance of your microcontroller family of 8051. Which particular instance you will implement will be dictated by your requirement. So, what we say, we use a part of the FPGA to implement a microprocessor soft core and can synthesize nearly any soft core to an FPGA fabric. And some vendors, even when they provide the soft core approach, say provide also processors tuned to their fabric. I have just picked up one example, Xilinx MicroBlaze, which provides a soft core for a 32-bit RISC processor, That means you can actually, if you are looking at a platform instance, will be searching around this basic architecture, some variant of this basic architecture to meet your requirement. Because this is typically provided as a VHDL or Verilog structural source. Verilog is another language equivalent to that of your VHDL, hardware description language. So, this is a typical way this is done in a soft core approach. So, if you look at the basic structure of this MicroBlaze soft core architecture, you will find that this is basically the processor configuration. This processor configuration and the processor logic, how it would work, everything should be available in a VHDL form. Along with it, you have got peripherals. So, numerous integrated on-chip peripherals and on-chip memories have been provided here. So, here what you find that there is an on-chip data memory. You have got this part is your actual architecture, the control unit, instruction buffer, program counter, machine status registers, register file, and these are variety of peripherals which are available, and you can configure the whole system, as a soft core and then implement for your embedded systems, So, in this case, the advantage is your search flexibility. That means, flexibility of the platform is much more compared to a hardcore approach, because you can actually play with the processor core itself to meet your requirements. On the other hand, the hardcore approach, in fact, the accelerator design is an example of exploitation of this hardcore approach. Many devices include hardcore, that means a processor, cache, RAM and configurable logic. So, in this case your memory architecture is also not available to you to decide. It is a kind of a fixed memory architecture. What is available is primarily is configurable logic. Compared to soft cores, it can be more area efficient because you are designing the processor once in the most efficient fashion, and leave more configurable logic for other uses, because in the other case the processor itself is consuming the configurable logic block. It can be faster because you can have an optimized implementation of the hardcore CPU, but trade off is obviously less flexible, can't choose arbitrary number of cores. In fact, in a soft core approach, I can actually choose multiple CPUs, and I might like to implement multiple CPUs depending on my requirements and map tasks onto these multiple CPUs. But those kind of flexibilities are not really here, because here this CPU is expected to control the basic operations. So, now with this background, let us look at actual design examples with the platform based approach. First, we shall look at an accelerator, a video accelerator, and this video accelerator is very common for any kind of an appliance which is doing a video compression. In fact, with the camera we had discussed the basic principle of image compression, what we do? We apply DCT to the image, then we do quantize, then we do entropy coding. When we are looking at that video analysis, okay, when we are having a video camera for that matter, we would like to design, which would store in the memory stick MPEG videos, then we need to implement in hardware the MPEG compression scheme. The MPEG compression scheme is conceptually similar to that of JPEG in various ways. The only difference is the MPEG also has to exploit what we call temporal redundancies. Okay. And to exploit temporal redundancy, they need to perform what is called block motion estimation. And that is the most compute intensive part of the video compression. So, we shall look at the problem of building an accelerator to do block motion estimation. In a way, this would perform a two-dimensional difference computation. Let us try to understand this problem. What is the problem of motion estimation? This is, say, this is a frame n and this is a frame n plus 1. Okay. Now, actually if you see, this part of the picture has moved almost in an unchanged fashion to this part. Okay. So, if I can know this shift with x and y, delta x and delta y shift corresponding to this block, then I need not encode this image afresh. I can reproduce this block from the previous frame. This is what is called the temporal redundancies in a video stream. Okay. And we would like to exploit this temporal redundancy for the purpose of compression. In fact, MPEG compression stream consists of what we call I, P and B frames. In fact, I frames are nothing but JPEG compressed frames. Okay. P frames are what are called predictively compressed frames. That means, for P frames, we actually exploit this kind of temporal redundancy. That means, the data in the current frame I can predict from the previous frame. And what we store in that case? We store these shift vectors and the error. The error is stored again like a JPEG image. We apply a DCT to the error, then we do quantization, then we do entropy encoding and store the error corresponding to P frames. When we have B frames means bidirectional coding. So, in that case, it may be possible for me to predict a window here from one of the future frames. That means, from the frame n plus 2, I can predict also backward. When we are using a combination of forward prediction as well as backward prediction, we get B frames. You can realize obviously that computation of B frames for the purpose of compression is computationally most complex. And in your video telephony, video conferencing kind of applications, we typically do not use B frames. We use I and P frames. So, when you use I and P frames, you can understand that DCT is obviously a time consuming block. And another time consuming block is this your motion estimation, because I have to actually search in this image to find a match for this block to exploit this redundancy. In fact, what I have shown here is a search area, the bigger block is a search area, okay, and I am mapping this block in the search area and I am moving around this block over the search area to find the best match. So, this computation is what I would like to accelerate. So, if we look at more technically, what we have got is that in MPEG the image is divided into what are called 16 cross 16 macro blocks. Now, these 16 cross 16 macro blocks have to be searched in the search area to find the best match. That means, I find the best match for the corresponding macro block. So, here in this image, if this is my reference picture, in the reference picture I have to search over the search area, okay, to find the best match for this block. Okay. So, what we are doing is the basic idea is if I consider this leftmost corner as anchoring point for the macro block, then this is giving me the shift, okay, x plus u and y plus v. Actually, I am interested to store u and v, which minimizes this error. Okay. I would like to store u and v, which minimizes this error. So, that would give me the motion offset, and I need not store the data, actual pixel data. So, we have to search around this, and at each position, therefore, at each position of this anchoring point, I need to compute this function. Fine. This is actually an absolute error, okay, summation over absolute error over each pixel in the macro block. Is this clear? And I would like to find out u and v, which would minimize this. So, what is the algorithm to be used? We are considering here the most inefficient algorithm, what we call a full search algorithm. That means, you search for the best match within the search range and search at each position, that means, compute the match score for each position of the block. Okay. So, I shall shift x y to each pixel position over the search area, okay, and compute the match score, fine, and then find the location with the minimum error. So, this is the algorithm, the least efficient algorithm, which is called full search algorithm. Now, one point you should keep in mind is that this searching algorithm is not part of the standard. So, if you are making a video camera, and if you can do this process well and fast, that means your camera is better compared to your competitor's camera, and both the cameras are at the same time compatible to your MPEG standard. And that is one of the reason and the motivation behind looking at different algorithms as well as hardware implementation for solving this problem. In fact, same thing is true for DCT computation also. The standard talks about using DCT, but what is the algorithm, what is the hardware algorithm to be used for computing DCT is not part of the standard. Okay. So, you have the option to innovate and get better design for developing this kind of embedded systems. And in fact, the whole idea comes from why we are talking about a platform based design. Platform fixes up certain aspects are open. The standard fixes up certain aspects are open. So, you can exploit the open part, get a better design on a platform. So, what is the computational requirements? MB size is typically 16 cross 16 and say search size is over 8 cross 8 window. So, your search area is 8 plus 8 in each dimension. So, therefore, you need to perform how many operations? 16 cross 16 into 17 cross 17 operations. This operation is actually difference computation operation. And typically a CIF format, which is a smaller format frames, has got 352 into 288 pixels, which translates to 22 into 18 macro blocks. And if for each macro block, if this computation is to be done, you can realize how many times therefore this difference is to be there. So, that is the basic time consuming part of the compression scheme, and this is to be built on FPGA block for high speed operation. So, let us look at the basic design. If we are coming from a pure object oriented approach, we have to identify the basic data types for doing this computation. Data types are what? The motion vector, macro block and the search area, fine. These are in fact the classes, okay, or the objects which we will be using for doing the computation. These classes will also encapsulate the hardware resources. So, I am showing a top level resource which is host processor along with the memory where the data will be there, and you have got a motion estimator which is actually the accelerator block that we are trying to design, and the operation, that is the request the processor will make, will be compute the motion vector. Now, this should be represented through a sequence diagram. Okay. So, you have got the host, this is an instance of the host, this is the instance of the motion estimator, this is the search area and the macro block. So, what you have got? So, the host actually makes a request to the accelerator for computing the motion vector. On receiving the request, the motion estimator should get the data about the search area and the macro blocks. So, I need to get the memory requests onto the hosts. So, it implies that is from the sequence diagram itself you can realize there has to be a substantial data movement between your memory and the FPGA block. So, what we say that requires large amount of memory. Macro block has got 256 pixels, search area is 1089 pixels. And if such a large memory transfers has to be done, that means your accelerator needs to be changed as well. So, you need external memory, especially if buffering multiple blocks as such areas is required. And that would be on the accelerator external to the FPGA block, but that memory is not part of the host memory. So, you may have a DMA block or DMA controller to transfer the data from the host memory to that of the memory on the accelerator block. So, this is one of a possible architecture. If you see here, this is the memory, macro block and the search area, this contains the data. This is a basic address generator, and these P's are implemented on the FPGA block. Each P does what? Perform absolute difference computation for a pair of pixels, and your comparator takes the data from the PE, okay, integrates this together and produces the motion vector corresponding to the base value. Okay. The interesting thing is that this is a network which connects the data from the macro block and the search area to the PE depending on how the scanning is taking place, because you are scanning the macro block over the entire search area. Depending on the scan, this interconnection has to be done, and which data is to be selected is given by the address generator. So, address generator is actually taking care of the scanning task. So, if you want to implement a different algorithm from full search, the address generator logic has to be different, okay, and that then it can implement a different logic. You might not like to search at each pixel, you might like to sample and search. Okay. So, this becomes the basic organization in terms of the FPGA block. So, the pixels, how they are scheduled, because that scheduling is as an important factor for doing the design. If you see that if I have P0, P1 and P2, from the macro block I can have 1 pixel from macro block memory and 2 pixels from search block memory, and if they are distributed, these operations can be scheduled simultaneously. Okay. So, I can have same pixel coming in and I can do this computation, okay, and therefore, these pixels are distributed in a regular pattern, and this distribution is done with the help of the network, okay, and that organization is a key issue in terms of this design. Okay. So, here you will find that S02 how it is taking care of this same data. This is your same S02, and I can use the same data over multiple macro block pixels, and these macro block pixels are traversing along the diagonal path over the P's. Okay. So, that traversing and fetching regularity pattern gives you the efficiency in computation. Now, we shall look at very briefly another example with the network platform. This problem is that of designing a sensor network with platform based approach. So, if you are talking about a network platform, a platform instance will be a set of resources, links and protocols that provide communication services. You got to have a network platform API for providing a set of communication services. and set of communication services is mechanisms to be used to transfer messages between ports, because these are the elements which had to be used to characterize your network platform. So, your network platform talks about a variety of possible instances of the resources that we will be using. So, let us look at a very simple example. So, if I have a network platform API by which you can make a choice about your network components, nodes, links and ports IO, what you will be doing? You will be actually deciding upon a configuration and a protocol using the API. Mapping onto that will give you a network platform instance. You do a performance estimates on that network platform instance, see whether your budgets constraints are getting satisfied or not. So, that means when you are doing the API, okay, through the API specifying the architecture, because specifying the architecture primarily would mean specifying the communication services architecture, that is the different protocols, okay, and with these protocols and the constraints budgets, you get one particular network platform instance, and on the basis of that you get a performance estimate. So, one possibility could be, is it a single hop network or a multi hop network? If it is a multi hop network, then you might have a better energy estimate, you might have a better QoS. So, those things can be checked up, okay, through this API and have the complete distributed embedded system design. So, in fact, the reason for looking at briefly this example is to understand that distributed systems can also be designed through this platform based approach, because here your hardware elements are what? Your nodes, different parameters for the nodes, different parameters for your communication link. The software elements are your protocols. Everything put together with the budget constraints can be tried out, obtained a performance estimate, and that is basically your search in the possible space of alternative formulations to get and identify the optimal configuration for your network. Okay. So, what we have looked at therefore at platform based design approaches and consider design examples, this more or less brings us to the end of basic design schemes for embedded systems. In the next class, we shall look at some of the software related issues, particularly compiler related issues which can be used for optimal design.